Welcome back to Autonomous Insights, listeners. Today, we're diving deep into the intersection of two cutting edge fields: autonomous driving and large language models, specifically focusing on a groundbreaking paper that tackles the complexity of navigating urban environments. Joining me today are Dr. Hang Zhao, lead researcher and author of this fascinating work, and Emily, a veteran engineer in the autonomous driving industry. Welcome both.
Thank you for having me, Amelia.
It's great to be here. Let's get into it. Emily, before we jump into the details of this paper, could you give us a sense of the challenges facing autonomous driving systems today, particularly in urban environments?
Sure, Amelia. The biggest hurdle is interpreting the chaotic nature of city driving. We need systems that can understand not just static objects like cars and traffic lights, but also dynamic elements like pedestrians, cyclists, and even unusual objects that might not be in a typical training dataset. You can't train for every possible situation.
It's like teaching a kid to ride a bike in a bustling city park. You need to teach them not only how to ride, but also how to anticipate other people's movements, react to unexpected events, and be aware of their surroundings. Exactly. That's where this new research comes in. Dr. Zhao, could you tell us about DriveVLM and DriveVLM-Dual and how they approach this problem?
Our system, DriveVLM, leverages the power of vision language models, or VLMs for short. Think of it like a superpowered image search engine that can not only identify objects, but also understand the context of those objects. It can see a car, but it can also figure out if it's stopped at a red light, turning, or about to merge into the current lane.
So, VLMs can basically read a scene and understand the relationships between objects and their actions. That's fascinating.
Exactly. And DriveVLM has three key modules: scene description, scene analysis, and hierarchical planning.
Can you elaborate on those modules, Hang? What are they actually doing?
Sure. Scene description is the first step. DriveVLM describes the environment in detail, things like weather, time of day, road type, and lane conditions. This sets the stage for understanding the driving scenario. Then, it identifies critical objects, those that are most likely to influence the ego vehicle's decisions, and describes their locations.
So, if a car is driving normally, it wouldn't be a critical object. But if it's stopped in the middle of the road or about to turn across your lane, it becomes critical, right?
Precisely. Then scene analysis dives into those critical objects. It doesn't just track their movement, but it understands their characteristics, their static attributes, their current motion, and their specific behaviors. This helps DriveVLM predict how those objects might influence the ego vehicle's path.
Like if a car is stopped at a red light, DriveVLM wouldn't just see it as an obstacle, but it might also analyze that it's a red car, and that red cars in this location tend to be aggressive drivers. That kind of context is really helpful for predicting future actions.
Exactly. And the last module, hierarchical planning, takes all that information and builds a driving plan. It goes through three stages: meta actions, decision descriptions, and trajectory waypoints. Meta actions are high-level decisions like slow down, change lane, or turn right. Then, the decision description provides more detail, describing the specific action, the subject of the action, and the duration of the action. Finally, the trajectory waypoints specify the actual path the car should take.
It sounds like DriveVLM is doing a lot of heavy lifting, but how does it deal with the computational demands of this complex process in real-time driving?
That's where DriveVLM-Dual comes in. It recognizes that VLMs, while powerful, can be computationally intensive, which makes them less than ideal for real-time scenarios. So we combine the strengths of DriveVLM with a traditional autonomous driving pipeline. This pipeline has modules for 3D perception, motion prediction, and trajectory planning, but it relies more on traditional methods for processing information.
Think of it like a two-brain system. DriveVLM is the thinking brain, analyzing the scene and making high-level plans. The traditional pipeline is the doing brain, refining those plans and executing them in real time. That makes sense, and this dual approach seems to be working really well. Hang, what are some of the key findings from your research?
We tested both DriveVLM and DriveVLM-Dual on our own SUPAD dataset, specifically designed for complex driving scenarios, and also on the publicly available New Scenes dataset. DriveVLM outperformed other vision language models, especially in situations involving uncommon objects or unexpected events. We also found that DriveVLM-Dual achieved state-of-the-art performance on the new scenes planning task, showing that it can handle not only challenging scenarios, but also more typical driving situations.
Those are impressive results, Hang. But Emily, as an expert in the field, what are your thoughts? Do these findings have the potential to really revolutionize autonomous driving?
I'm cautiously optimistic, Amelia. This research shows a promising path forward for improving scene understanding in autonomous driving. It's great that DriveVLM can handle those long-tail scenarios, which are a huge concern for real-world deployment. However, we still have a lot of work to do. We need to ensure that these systems can function reliably in a variety of conditions, including diverse weather, lighting, and road types. We also need to develop more robust evaluation methods and address the computational challenges of running these models in real time. And I think it's important to remember that this is just one piece of the puzzle. We still need advances in other areas like perception, motion prediction, and control to make fully autonomous driving a reality.
Hang, what are some of the key limitations of your current research? And what are some of the future directions you see?
You're right, Emily. We acknowledge that our dataset, while diverse, still needs to be expanded to include more edge cases and even more varied environments. We also need to continue improving the evaluation metrics, ensuring they fully capture the nuanced aspects of driving decisions. Looking ahead, we're focused on developing better ways to integrate VLMs into existing autonomous driving systems, optimizing them for real-time inference, and exploring the potential of VLMs for more advanced decision-making, like understanding traffic signals, predicting the intentions of other drivers, and even anticipating potential hazards before they occur.
It sounds like this is just the beginning of a very exciting journey in autonomous driving. Hang, Emily, thank you both for sharing your insights. This research is truly groundbreaking, and I'm sure it will have a significant impact on the future of transportation.
You're welcome, Amelia. It's been a pleasure to discuss this research with you and Emily.
It's been fascinating. I look forward to seeing how this technology develops in the years to come.
And listeners, make sure to check out our website for more information on this research and other exciting developments in the world of autonomous driving. Until next time, keep driving safely.